Okay, my first of all, I wish to thank you the organizing committee. Thank you very much for the opportunity of giving this talk on this great workshop. Okay, I'm going to talk today about the detection of planetary transits candidates using the VVV and VVVX photometric data. So my data, and I'm using the VVV and VVVX that was previously shown in the previous grade talks of my colleagues and my supervisor, the Saito. And we are using the infrared and VISTA telescope. Okay, first of all, the perspective on exoplanetary transits and exosolar planets on VVV was on 2011 for Saito. He raises these perspectives with this simulation. So he wished to think how a light curve on VVV should be for exoplanet. And he made a simulation using, actually he made two simulations. Here's the first one. He used 2.8 days for period and two options of stars. One using 14.5 magnitudes on the inner bulge, and the other one uses 16 magnitudes on the outer bulge. So on the outer bulge, we can have a much fainter source. Also, this simulation gets for two options of exoplanets. It can be a Jupiter orbiting a G2 star on 1.4 kiloparsec, or a super Earth orbiting an M6 dwarf 100 parsecs far away. So you can see here is the MG time modified during date, and here is the phase folded. This is the first simulation that I told, because on VVV you have overlap tiles. So this was the original idea from VVV with 8-9 data points. Now we have much cadence on with the VVVX, and we can go to 300 points on the inner bulge. And this is the overlap light curve. And you can see here the trend. So this was the start of the perspectives. Okay, for the start of the search, I made a research of the already know exoplanets on the VV field. So this is the map, and we have 814 exoplanets that was discovered on the VV field. And from these, we have 2010 with photometric data on the VVV. The blue ones are the confirmed exoplanets, and the green ones have the photometric data. And these red ones, I hope you can see, is the one discovered by transit. So the idea of the search is search for transits and transit candidates, but we have only 11 planets discovered by transits on the VV field. We have this huge amount of planets here on the inner bulge, but they're discovered by OGO, by microlensing on the inner bulge. So we are not working with them. Okay, this data was taken from Exoplanetary Archives in September 23, so it's actually very new. Okay, this is a color magnitude for these exoplanets on the VV field. We have the green ones that were discovered have photometric data, the 210, and the red ones have the trends. So we have below upper from 13 magnitudes into 17 magnitudes. This is going to be important for the sigma limitation that I'm going to talk after. Here are the 11 of them, but I couldn't work with all of them because from these 600 to the 1088, it's VVVX tiles. So I don't have the PSF for photometry yet. We are working on this, so I work only with these first four ones that are sweeps and OGO exoplanets. Here we have the orbital period for them. So I talk about the sigma limitations, and here we have a plot from our sigma error and for the magnitude. So this is a inner bulge and outer bulge plot. And you can see that in the inner bulge, you have much greater dispersion, increasing speed starting off the magnitude of 13. So we are working on this inner bulge and the BADS window. So we can see that here we have a much dispersion and it becomes hard to search on the exoplanets after 13 magnitude. But on the our budget here on B40 401, we have a much fainted here. Actually, this is a PSF photometry from Javier. Thank you. Okay, now we have the light curves from these four exoplanets we already know, but we can get any transits here. So I got to look on the paper ones or on the light curve on the paper that was taken. But we have a situation that this one are from sweeps and from Argo, and these sweeps were discovered like I think 10 or 14 years ago. So we have a lot of time for the Zeitkov. So we can get anything from it. If you are very optimistic, you can see some points here and here, but nothing actually really good. So we can recover the original light curve. So we have the three ones here from sweeps 110, and that's another thing that these exoplanets have a little magnitude depth, so it can be a reason. Okay, but this was just a challenge. It was not a no. Like, this was a challenge, and we accept the challenge and begin our search on the three tiles from the inner bulge, the 307, 293, and 394. We limit our search on M dwarfs on the M dwarfs, so we can have a bigger depth on the transit. So we start with the color code selection here on the tile. This is the 307 tile, and we have the color magnitude diagram. And we use Hoyos-Ayala equation to get the M type of this stuff. Here's a magnitude distribution, and we can see that our magnitudes of the M dwarfs are much higher than we expected. It's not expected, but what we want. So here we actually need something between 12 and 13, maximum 14 magnitude, but we have a huge amount of stars on this magnitude between 14 and 17. But it's another challenge, and we keep going. So this we have 5,200 sources that we selected, and we made a color cut, distance cut too, using one capacity of distance. And this part was made by Thiago Ferreira, a colleague from Brazil, and he made a box lead square selection for the variability. So I'm not into this part, I'm sorry, but he made a BLS selection, and he got 141 variable sources between on this amount of MDOF stars. Okay, we use planetary parameters, so the depth was 2% and less than 2%. Okay, so now we have the MDOFs, we have the variable ones, and we're gonna search for the planets. So we have this variability check from BLS, only search from the period. So we get the period, and you know they're variable. So I use the Batchman. It's a basic transit model calculation in Python by Laura Kimberg of Harvard. And this package, it's a modeling exoplanet transits and light curve. So I take the period from the box lead square and calculate with the 7 parameters the Batchman light curves. But this Batchman is not made to plot against the data points. It's just a modeling light curve. So I made a modified Batchman that now get the period from both its squares, and I got on the time input I put the phase or the model due date, depends on the data on the Batchman. So now he plots one data point of the of the expected light curve from each of the real data points. So now I can plot on the theoretical light curve based on the period from both least squares from the real data points and calculate how much they fit. So we can do this automatically. This is the idea with the VVV. Since VVV is a um, wide, it's a wide field survey, we can make this automatic for every tile if you want. This is the idea, to make for every tile and automatically get the good fitting of the points on the light curve. So here we have one light curve for each tile that we search, and the final search get us 9 candidates of exoplanets. So we have 62,000 M dwarfs. We had 141 variable ones, and we get 9 good fitting with Batchman modifier. So this is the first one from B294, and we have here the transit. Here's from B293. We have here the transit 2, and for the B207. And something that's very nice to see is the radius of the planet. It can be a Jupiter here, close to Jupiter, and this one 2, and this is a 2 times Jupiter. So it's great to know we can find. It would be great to find this kind of exoplanets on M dwarfs. Okay, so the next steps on this search is make differential photometry, because we're not using differential photometry, we're using all-sky photometry from PSF, from Contreras. We think it's gonna get very better with the differential photometry. It's very essential to do it with these and for the previous ones. We're gonna do first on the already discovered exoplanets to see how better it goes, and then with the 9 candidates we find on these 3 trials. The two thing after the differential photometry, we're going to expand the curve method for the other tiles. So we made first on the 3 tiles because they are not enabled, you have high cadence, was the great cadence on the VVV. So we made on the 3s, but the idea is to expand for the average tiles. We have a good cadence. And the 3 steps is going to follow up on these 9 candidates and see if there's good candidates, if you can confirm, or if it's just error and noise. And that's it. Thank you very much, and thank you for the opportunity to talk.